something both strange and unsettling is unfolding above us. Harvard scientists have just announced that Comet 3I Atlas, already one of the most mysterious interstellar visitors in human history, is far more massive than anyone expected. The numbers are staggering. At least 33 billion tons of mass. That's not just a comet, but a cosmic monster. Imagine a body so immense that sunlight boils its surface, yet the jets of gas cannot shift its gravitational path by even a fraction. And that raises questions. Big questions. If this object is so much larger, what does that mean for us? Could it imply hidden populations of colossal debris drifting silently between the stars? Or, if we dare to ask, could it hint at something stranger still, perhaps even artificial construction cloaked in ice and gas? These are the questions Atlas forces on us. Science explains much, but this comet refuses to play by the rules. Stay with me as we embark on a voyage through science, speculation, and wonder. Together, we'll explore why Harvard scientists are baffled and what hidden secrets might be lurking behind this sudden leap in size. Let's begin. When Harvard scientists released their findings, one detail stunned the astronomy community. Atlas is so massive that its path remains almost untouched by the sublimating gases pouring from its surface. That lack of measurable push implies a bulk greater than anyone had modelled before. In the world of comet science, this is deeply unusual. Most comets are fragile, porous bodies, ice-rich remnants that respond visibly to the faintest of nudges. As the sun's warmth liberates gas from their frozen cores, these jets act like tiny thrusters, producing measurable deviations in orbit. For astronomers, such deviations are expected, even relied upon, as part of the delicate balance that helps calculate a comet's mass and structure. But with 3I Atlas, the expected dance is strangely absent. The jets are there, the coma is bright, and yet the comet moves as though nothing at all is happening. The Harvard team, led by Avi Loeb with Richard Cloaked and Peter Verres, framed this absence as a powerful clue. By comparing 3I Atlas's observed trajectory with the path predicted, if only gravity were at work, they found the two nearly identical. If sublimating gases are failing to shift it, then the comet must be overwhelmingly massive, too heavy for such forces to make a difference. This transforms 3I Atlas from a mere visitor into something closer to a drifting mountain, a bulk of billions upon billions of tons carrying the memory of another star system. Consider the scale implied. Imagine a solid block of material kilometers across, heavy enough that the steady exhaust of hundreds of tons of gas per second cannot alter its course. This is the cosmic equivalent of a feather brushing against a boulder. The force exists, but the object it pushes is far too immense to notice. The silence of non-acceleration becomes its own message. Atlas may be the most massive interstellar wanderer ever studied. Such weight forces astronomers to confront uncomfortable questions. If one comet can be this large, how many more like it are adrift between the stars? Are they rare anomalies, or representative of a hidden population of giant bodies that galaxies routinely cast off? If common, then our models of planetary formation and ejection underestimate the true abundance of interstellar debris. And if rare, then why did one appear now, passing through our neighborhood at precisely this moment in cosmic history? Skeptics counter with caution. They argue that estimating mass from the absence of acceleration requires many assumptions. Assumptions about how much gas is escaping, at what velocity, and in which directions. A smaller nucleus with uneven jets could, in theory, mimic the same result. But even with these caveats, the Harvard team insists the numbers leave little room for a lightweight solution. Something about 3I Atlas defies the expected template. It is here, in the tension between certainty and uncertainty, that science becomes most intriguing. A comet that refuses to yield to its own jets hints at more than just hidden heft. It reminds us that the universe is stranger than our models, more diverse than our expectations, and always ready to surprise. Atlas drifts on, indifferent to our debates, but carrying with it the weight of questions that will linger long after it has vanished back into the interstellar dark. Most comets wobble under the gentle thrust of their own jets, yet 3I Atlas does not. Its motion is stubborn, unyielding, as though something unseen anchors it in place. For centuries, astronomers have watched the sky's icy wanderers perform this subtle dance. As comets warm under the sun's glow, pockets of frozen gas within them erupt outward, releasing streams of vapor and dust. These jets, though faint compared to earthly engines, act like miniature rockets, pushing and twisting the nucleus ever so slightly. Over weeks or months, such forces add up, and a comet's orbit begins to show tiny but measurable deviations. It is a graceful, natural rhythm, a fragile object reacting to the heat of a star. But 3I Atlas breaks that rhythm completely. Despite its coma expanding into hundreds of thousands of kilometers of glowing haze, despite the torrents of carbon dioxide erupting from its depths, this interstellar traveler does not flinch. No matter how closely astronomers measure, its trajectory aligns almost perfectly with the predictions of gravity alone. It sails on, indifferent to the very outgassing that should buffet it. Like a ship resisting the wind, it moves as though some unseen ballast pins it in place. This refusal to be moved is not merely aesthetic, it is data. It tells us that beneath the bright fog and streaming tails lies a body of extraordinary inertia. To resist its own jets, the nucleus must be massive, perhaps several kilometers across, with a density or structure far greater than imagined. Harvard's analysis suggests the comet's weight dwarfs that of most known interstellar candidates, making it a cosmic anomaly. And anomalies invite speculation. Could the explanation be simple, that the comet is larger, heavier, denser than expected? Or is something else at play? Some whisper of exotic scenarios? A hollow shell concealing denser material, or even artificial reinforcement, a construct that resists the push of escaping gases by design. While these ideas stretch far beyond accepted models, the silence of movement tempts the imagination. But even the natural explanations are profound. A comet this unmoved may carry clues to the earliest epochs of planetary formation. Its resilience could hint at origins in a particularly extreme environment. Perhaps the outer regions of a star system where carbon dioxide froze in abundance, or even in the gravitational chaos near a dying star where denser cores were born. In refusing to wobble, 3I Atlas is telling us about the conditions that forged it, conditions likely very different from our own solar nursery. There is a quiet beauty in this defiance. Where other comets twitch and shift, this one glides straight, as if honouring some older, deeper trajectory carved long before our sun ever existed. Its stubbornness becomes a symbol of endurance, a relic of another time and another place, still holding to its path after billions of years in the interstellar dark. As we drift with it in thought, we are reminded that not all visitors follow the rules we expect. Some, like 3I Atlas, refuse to be moved, and in that refusal, they force us to expand the boundaries of what we think possible. Astronomers often learn from what is missing. In this case, it is the silence of acceleration, the absence of deviations, that whispers the comet's true size. In science, what we do not see can be as important as what we do. The orbits of planets, the faint tugs on starlight, even the quiet shadows of gravitational lensing all reveal hidden truths. With 3I Atlas, the revelation comes not from dramatic fireworks, but from stillness. Despite its active jets venting carbon dioxide and dust into space, its path remains undisturbed, as though carved by an invisible hand. The Harvard team seized on this subtle clue. By plotting the comet's trajectory with exquisite precision, they compared its actual course with the predictions of pure gravitational motion. If the jets were nudging it, even slightly, the orbit would deviate from that path. Yet it did not. The difference between expectation and reality was smaller than the width of a human hair measured across hundreds of millions of kilometers. That absence of measurable acceleration became a kind of cosmic equation, one in which the unknown variable was mass. To resist acceleration, an object must carry weight. The heavier it is, the less it responds to the same force. If 3I Atlas can shrug off the push of sublimating gases, then its nucleus must be vast. Estimates suggest a lower limit in the tens of billions of tons, a staggering figure that transforms this comet from a fragile snowball into a fortress of interstellar stone and ice. This approach, though indirect, echoes the methods used across astronomy. Astronomers measure exoplanets by the wobble of their stars, detect black holes by the light they do not emit, and estimate galaxy masses from the invisible pull of dark matter. Silence is not void, it is a different kind of signal. And here, the silence of acceleration is speaking loudly about the hidden heft of an alien visitor. Of course, such inferences invite debate. Critics argue that estimating mass from a lack of movement depends heavily on assumptions. What if the gas jets are weaker than expected? What if they vent unevenly, cancelling one another's thrust? Could a small, lightweight nucleus masquerade as a giant simply because its activity is oddly balanced? These counterpoints remind us that silence can sometimes mislead, and that nature often finds ways to play tricks on human perception. But even with such cautions, the consensus is growing that 3I Atlas is at least extraordinarily heavy. If not uniquely so, its behaviour stands apart from every other comet we have studied. Whether it is 10 times heavier than expected or 100, the implications ripple through our understanding of how interstellar debris forms, survives, and drifts through the galaxy. There is a haunting poetry in this. Imagine standing in a quiet forest and noticing not the rustle of leaves, but their stillness, the way they refuse to stir even as the wind blows. That is what astronomers see when they track 3I Atlas. The gas jets hiss, the coma expands, but the nucleus remains unmoved. From that silence, we are left to calculate the weight of an ancient traveller, a silent messenger from another sun, telling its story not through motion, but through refusal. The lower limit proposed is staggering. Tens of billions of tons, enough mass to make the comet's tiny nucleus a mountain adrift in space. When we imagine a comet, we often picture something fragile and fleeting, a dusty snowball that streaks across the night sky, its tail dissolving like mist. Yet 3I Atlas challenges that image. At its heart lies a nucleus so heavy that the numbers boggle the mind. Billions upon billions of tons bound together, packed into a body that drifts silently through the void. It is, in essence, a piece of another world, a fragment of planetary construction flung loose from a distant star system and set on a journey lasting millions of years. To picture such weight, consider Earth's tallest mountains. Mount Everest rises nearly 9 kilometers into the sky, its mass composed of countless rocks, ice, and layers of ancient stone. Now imagine a mountain like that, shrunk into a compact sphere, cold and dark, sailing through interstellar space. That is the vision scientists evoke when they describe the scale of 3I Atlas's nucleus. What makes this all the more extraordinary is the way it hides its size. To our telescopes, we do not see the nucleus directly. Instead, we see the glowing coma, a cloud of gas and dust expanding for hundreds of thousands of kilometers, lit by sunlight. The nucleus itself remains shrouded, hidden within that haze, a mountain veiled in fog. Only through indirect measures, through the silence of its unmoving path, through the analysis of its chemical output, do we begin to glimpse its true form. This hidden mountain forces us to rethink how interstellar objects might form. To build such a mass requires extraordinary conditions. Perhaps the cold outskirts of a planetary system, where frozen ices accumulate for eons, or perhaps the violent outskirts of a forming world where collisions fuse rubble into denser cores. Whatever the birthplace, it must have been a crucible capable of forging giants. And yet, for all its scale, 3I Atlas remains vulnerable. The gases venting from its surface, the fractures etched into its skin, remind us that it is not indestructible. Like a mountain carved by wind and rain, it will erode as it draws closer to our sun, shedding billions of tons of dust into space. Its tail will stretch across millions of kilometers, and yet the mountain at its core will remain largely intact, an unyielding heart of ice and rock older than human history. Speculation creeps in here as well. Could such mass, hidden beneath a cloak of gases, conceal something more exotic? Could what looks like a comet be something engineered, its weight deliberate, its resistance purposeful? While mainstream science leans toward natural explanations, the very scale of the object invites more adventurous ideas. After all, the galaxy is vast, and the possibilities it holds are greater still. For now, what we know is enough to inspire awe. 3I Atlas is not a feather drifting on cosmic winds, it is a mountain in motion, a monument of mass carried across the stars. Hidden in darkness, it whispers of distant worlds and reminds us how small we are in a universe where even comets can rival mountains. Avi Loeb, Richard Cloé, and Peter Veris work together to piece the puzzle. Their methodology is controversial, but their results cannot be ignored. Each of these scientists brings a different thread of expertise to the tapestry. Avi Loeb, well known for both bold ideas and willingness to step into controversial territory, has long argued that interstellar visitors may not all be natural. His writings on Oumuamua sparked headlines around the world, raising the possibility of artificial origins. Richard Cloaked and Peter Veris, both deeply grounded in orbital dynamics and the study of near-Earth objects, had the mathematical rigor to track Atlas with precision. Together, they form a team balanced between caution and provocation, an alliance that invites both excitement and scrutiny. Their study did not rely on new telescopes or dazzling images. Instead, it was a careful comparison of numbers. They plotted Atlas's course over months, matching its observed position to the path gravity alone would predict. If jets of escaping gas were altering its motion, even slightly, the deviations would accumulate, yet the data showed none. It was as if the comet had shrugged off its own exhaust, sailing on unperturbed. From this absence, they drew bold conclusions. The comet must be massive, far heavier than conventional wisdom would suggest. Using estimates of gas loss rates and outflow speeds, parameters refined by the James Webb Space Telescope, they calculated a minimum weight in the tens of billions of tons. Such numbers lift Atlas out of the category of fragile snowball and into something more enduring, something with a gravitational presence all its own. Of course, bold claims bring resistance. Many astronomers point out that the assumptions baked into the equations are uncertain. Outflow speeds vary, mass loss rates can be patchy, and jets do not always behave symmetrically. Critics warn that a smaller nucleus could still explain the data if its activity were unusually balanced. The Harvard team acknowledges these caveats, yet maintains that the simplest explanation is also the most dramatic. The comet is simply bigger than expected. Avi Loeb, in particular, is no stranger to such debates. Some hail him as a visionary willing to ask uncomfortable questions. Others see him as a provocateur, pushing speculative interpretations too quickly into the public sphere. By raising the stakes, by framing the comet as anomalously massive, he forces the scientific community to wrestle openly with possibilities it might otherwise set aside. Cloaked and Veris provide the stabilizing counterpoint. Their precision in orbital mechanics grounds the argument in hard data. By carefully modeling gravitational forces, solar influences, and observational uncertainties, they anchor the team's conclusions in measurable reality. The interplay between Loeb's imagination and their rigor gives the study both its weight and its controversy. In the end, whether one agrees with their interpretation or not, the Harvard team has shifted the conversation. Atlas is no longer just another comet, it is a question mark written across the sky. Their paper invites us not only to measure, but to wonder, what does it mean if interstellar visitors can be this massive? And what else might be out there, still waiting to be discovered? Normally, sublimating ice acts like a rocket engine, changing a comet's course. For Atlas, that engine sputters uselessly against overwhelming mass. This process of outgassing is one of the most beautiful and delicate engines in the universe. Picture frozen carbon dioxide, carbon monoxide, and water ice buried within a comet's nucleus. As the comet approaches a star, solar radiation seeps into its surface, warming those frozen reservoirs until they leap suddenly into vapor. The gas bursts outward through cracks and vents, dragging tiny grains of dust along with it. From Earth, we see this as a shimmering coma and a glowing tail, but to astronomers, it is also a form of propulsion. For most comets, this propulsion is unmistakable. Outgassing produces a steady push, like the exhaust of a spacecraft, causing measurable accelerations that alter their orbits. A comet might arrive slightly earlier than predicted, or veer a fraction of a degree off course. Over time, these shifts become significant, reshaping its trajectory through the solar system. It is a subtle but undeniable reminder that comets are not passive passengers of gravity. They are active bodies, responding to sunlight with every breath of gas. Yet with Atlas, the familiar dance is missing. The outgassing is there, telescopes confirm it. The coma swells, the tails extend, the molecules fly into space by the thousands of kilograms every second. And still, the comet refuses to move. It is as though the rocket engine has been lit, but the ship does not budge. The thrusters fire, yet the mountain remains still. For Harvard's team, this is the crux of the mystery. If the comet's mass were ordinary, if its nucleus were just a kilometer or two across, then such jets should nudge it away from a purely gravitational orbit. The absence of measurable change suggests that Atlas outweighs the forces acting upon it. Its inertia is overwhelming, smothering the effect of its own cosmic engine. This revelation redefines how we think of interstellar comets. The analogy of outgassing as propulsion is so ingrained that its failure here feels almost eerie. It is like watching a bird flap its wings without rising, or a ship hoist its sails only to remain anchored. The expected mechanism of motion is present, but the outcome is missing. And that missing outcome speaks of mass far greater than any of us had anticipated. Skeptics urge caution. They note that jets can be directional, cancelling each other's thrust. A vent on one side of the nucleus might oppose another on the other side, creating balance instead of motion. If so, the silence of acceleration could be an illusion. But even here, questions remain. Could such balance persist for months across such distances? Or is the simpler answer that the comet is just too heavy to care? Whatever the resolution, the imagery lingers. Atlas carries within it an engine older than humanity, one designed not by intention but by physics, one powered by the light of the sun itself. And yet, as it breathes into space, it drifts on unchanged, a leviathan ignoring the whispers of its own exhaust. In the vast silence of space, even a comet's breath can tell a story. And this one tells us of a body too immense to be moved. The implications ripple outward. If Atlas is this large, how many other interstellar giants are moving unseen between the stars? Astronomy often feels like a game of statistics played across a canvas too vast to grasp. One detection hints at many more. When we spotted Oumuamua in 2017, it was the first interstellar object ever confirmed. Then came Borisov in 2019, followed by Atlas in 2025. 3 objects in less than a decade suggested that our galaxy might be teeming with wanderers. But Atlas adds a new dimension. Size. If this visitor is truly billions of tons in mass, it challenges the question of abundance. Are we surrounded not only by countless small shards of alien systems, but also by hidden mountains of rock and ice drifting silently between the stars? If so, the galaxy may be more crowded than we imagined. Planetary systems fling debris outward as they form, their gravitational slingshots hurling countless fragments into interstellar exile. We once thought the majority of this material would be small, fragments the size of boulders or small hills. But Atlas suggests otherwise. If even a fraction of these exiles are as large as mountains, then the total mass of interstellar debris is staggering, a reservoir of material far greater than our models predict. This realization forces us to reconsider the risks and opportunities such giants pose. On one hand, massive interstellar bodies represent hazards. Their paths are unpredictable, their arrivals sudden, and their energy immense. A collision with a planet would release forces beyond imagination. On the other hand, they are also opportunities. Natural probes carrying the chemistry of distant stars, ancient archives drifting into our reach. By studying them, we can learn not only about their own formation, but about the diversity of planetary systems scattered across the Milky Way. And then there is the question of rarity. Perhaps Atlas is not typical at all. Perhaps it is an outlier, a once-in-a-billion visitor whose size is an accident of history. If so, its arrival in our era is a cosmic gift, a rare chance to study something almost never seen. If we have already seen one giant, might there be others, waiting quietly in the dark? Size matters because it changes the equation of survival. They drift for millions, even billions of years, unbothered by cosmic radiation or collisions. Their bulk protects them, ensuring they carry unspoiled clues about their birth environments. A mountain-sized comet is more than just a traveler. It is a time capsule from another world, shielded by its own enormity. In the silence of deep space, we cannot yet count how many of these giants roam unseen. But Atlas reminds us that size is not just a number, it is destiny. It decides what survives the journey, what stories reach us across interstellar gulfs, and how fragile or enduring each fragment of the cosmos can be. And as we drift into sleep, we are left with a haunting question. How many other hidden mountains are out there, waiting for us to notice them at last? Unlike the slender mystery of Oumuamua, Atlas appears heavier, steadier, and more comet-like, but also vastly stranger. When Oumuamua was first spotted in 2017, it sparked both wonder and controversy. Its shape seemed elongated, perhaps like a cigar or a flattened shard, and it displayed an odd acceleration that couldn't easily be explained by gravity alone. For a time, the world debated whether it was truly natural or perhaps something artificial. A probe, a relic, a fragment of alien design. The object slipped away before the questions could be answered, leaving a lingering sense of mystery in a scientific community divided between caution and speculation. In contrast, Atlas carries itself differently. It does not dart or tumble erratically. It does not glide with the delicate acceleration that unsettled astronomers studying Oumuamua. Instead, it moves with calm weight, resisting every push, as if anchored to its trajectory. Where Oumuamua seemed elusive and almost playful, Atlas feels monumental, a presence rather than a ghost. And yet, the comparison is not as simple as natural versus artificial, comet versus enigma. For while Atlas shows the signs of a comet, the coma, the tails, the outgassing, it is precisely the scale of these signs that unsettles scientists. The coma is rich in carbon dioxide, brighter and more expansive than expected. The tails shimmer with unusual chemistry. Its refusal to respond to outgassing is not just different from Oumuamua, but different from any comet we know. Both objects, in their own ways, defy the categories we try to place them in. The contrast deepens when we consider what each represents about interstellar space. Oumuamua was light and fleeting, a whisper of something fragile hurled from a distant system. Atlas, by contrast, is heavy and enduring, a monument of ice and stone that has survived eons of travel. One taught us that interstellar visitors exist, the other teaches us they can be giants. Taken together, they paint a picture of staggering diversity, a galaxy filled with wanderers, each carrying secrets of its birth. Speculation thrives in the space between these comparisons. If Oumuamua's strange acceleration raised whispers of technology, then Atlas's immense size raises its own questions. Could these objects represent different classes of travelers, some natural, some not? Or are we simply seeing the breadth of what nature can create when stars form planets and fling their remnants into the dark. Even in their differences, both objects share a common theme. They remind us how unprepared we are for the true variety of the cosmos. For centuries, we assumed our solar system was the template, its comets and asteroids the standard. But with each interstellar visitor, that assumption crumbles. The truth is larger, stranger, and more complex than we dared to imagine. And so the comparison between Oumuamua and Atlas is not just about shape, size, or chemistry. It is about perspective. One was a fleeting mystery, the other a stubborn giant. Together, they hint at a universe that refuses to conform to our expectations. A universe where every visitor is a reminder of how much more there is to learn. Borisov resembled a normal comet, but Atlas, with its weight and scale, feels more like a disruption to the rulebook. When Gennady Borisov, an amateur astronomer in Crimea, first spotted Borisov in 2019, the excitement in the scientific community was palpable. Here was our second confirmed interstellar visitor, and unlike the enigmatic Oumuamua, this one looked familiar. It had a bright coma, a long tail, and behavior that closely matched the icy wanderers born in our own solar system. For astronomers, it was a moment of reassurance. Interstellar space had delivered something strange with Oumuamua, but then it had also delivered something comfortingly normal. Borisov was the kind of comet we knew how to study. But Atlas complicates that comforting narrative. On the surface, it too wears the clothing of a comet, a vast coma, spectral lines rich with volatile gases, the iconic tails stretching out into the solar wind. Yet beneath that familiar appearance lies something profoundly unsettling. Its immense mass, its refusal to be shifted by its own outgassing, and its unusual chemistry tear open the rulebook that Borisov seemed to affirm. If Borisov was the ambassador of normalcy, Atlas is the herald of disruption. This contrast forces us to wrestle with possibility. Perhaps Borisov was not typical at all, but rather one end of a spectrum of interstellar debris. Perhaps Atlas is the other end, a reminder that the galaxy is not inclined toward uniformity. Planetary systems form under wildly different conditions, shaped by stellar winds, collisions, and gravitational chaos. If so, then the bodies they eject will be just as diverse. To expect sameness may be comforting, but it is a comfort that reality does not guarantee. In the shadow of Borisov, Atlas looms larger still. Atlas appears far more massive, with a nucleus potentially large enough to rival some of the biggest comets in our own system. If Borisov was a pebble tossed into the interstellar sea, Atlas is a mountain hurled across it. The scale difference alone suggests that we have barely begun to map the full diversity of interstellar visitors. And then there is the question of survivability. Borisov disintegrated quickly as it neared the Sun, crumbling under the pressure of heat and radiation. Atlas, by contrast, seems to endure, shedding gas and dust without altering its course, holding itself together as though its bulk is armor against destruction. Where Borisov showed us fragility, Atlas shows us resilience. The two together form a kind of cosmic parable. One was a fleeting echo of the familiar, the other, a towering disruption of the expected. Both remind us that interstellar space is not empty. It is populated with relics from distant planetary nurseries, each carrying stories carved in ice and rock. Some will mirror what we know, others will force us to confront what we do not. In that sense, Borisov casts a long shadow, not because it was remarkable in its strangeness, but because it lulled us into believing interstellar visitors might conform to our expectations. Atlas emerges from that shadow like a revelation, reminding us that the universe thrives on surprise, and that every visitor rewrites the story we thought we understood. The leap in scale is not incremental, it is dramatic. Nature seems to be showing us the far edge of what interstellar debris can be. In most branches of science, change comes gradually. A new comet discovered here, a new asteroid measured there, each adding a small piece to the puzzle of our universe. Patterns emerge, laws are refined, and anomalies are gently folded into the story we already know. But every so often, nature discards subtlety and delivers something that feels like a shock. A data point so far from the expected range that it redraws the entire landscape. Atlas is one such point. Consider the sequence. First came Oumuamua, small, mysterious, oddly accelerated, a puzzle that leaned toward the delicate and the elusive. Then came Borisov, a comet that looked and behaved almost exactly like those born in our own solar system. Fragile but familiar. These two formed a spectrum we could understand. One strange, one normal, both within reach of our theories. And then, just when comfort began to settle in, Atlas arrived. Larger, heavier, far less responsive to the forces that shape every other comet we know. The leap is not gentle. It is a step change, a boundary crossed, a threshold revealed. What makes this threshold so striking is not only the size, but the implications it carries. If interstellar debris can be this massive, then our models of planetary formation must accommodate not just fragments and shards, but mountains. This is a universe that does not merely fling pebbles into the void, it hurls entire landscapes. The discovery stretches our imagination of what planetary systems can produce, and what interstellar space might truly contain. The dramatic nature of Atlas also raises practical questions. If objects of this scale are moving silently between the stars, how many of them have already passed us by unseen? How many wander through the galaxy, invisible until chance places them against the background of our telescopes? A fragment a few hundred meters wide is hard enough to detect. A nucleus several kilometers across, cloaked in its coma, challenges even our best instruments. For every one we catch, there may be countless others gliding through the dark, unknown and unrecorded. In this way, Atlas is both a discovery and a warning. It tells us that the cosmos is more extravagant than our cautious models predicted. It reminds us that our knowledge is provisional, built not on certainties but on the limited sample of what we have seen. The threshold it reveals is not just about comet size, it is about the limits of our perception. We thought we knew the scale of interstellar debris. Now, we realize the scale is larger, stranger, and perhaps only beginning to be understood. For the dreamer, this threshold is exhilarating. It suggests a galaxy alive with diversity, filled with travelers of every shape and size. For the scientist, it is humbling. It calls for new models, new surveys, and new questions about the distribution of matter in our galaxy. And for the rest of us, it is a reminder of the simple truth that keeps us gazing upward. The universe will always exceed our expectations, always find a way to reveal thresholds we did not know existed. The leap in scale is not incremental, it is dramatic. Nature seems to be showing us the far edge of what interstellar debris can be. In most branches of science, change comes gradually. A new comet discovered here, a new asteroid measured there, each adding a small piece to the puzzle of our universe. Patterns emerge, laws are refined, and anomalies are gently folded into the story we already know. But every so often, nature discards subtlety and delivers something that feels like a shock, a data point so far from the expected range that it redraws the entire landscape. Atlas is one such point. Consider the sequence. First came Oumuamua, small, mysterious, oddly accelerated, a puzzle that leaned toward the delicate and the elusive. Then came Borisov, a comet that looked and behaved almost exactly like those born in our own solar system, fragile but familiar. These two formed a spectrum we could understand. One strange, one normal, both within reach of our theories. And then, just when comfort began to settle in, Atlas arrived. Larger, heavier, far less responsive to the forces that shape every other comet we know. The leap is not gentle, it is a step change, a boundary crossed, a threshold revealed. What makes this threshold so striking is not only the size, but the implications it carries. If interstellar debris can be this massive, then our models of planetary formation must accommodate not just fragments and shards, but mountains. This is a universe that does not merely fling pebbles into the void, it hurls entire landscapes. The discovery stretches our imagination of what planetary systems can produce, and what interstellar space might truly contain. The dramatic nature of Atlas also raises practical questions. If objects of this scale are moving silently between the stars, how many of them have already passed us by unseen? How many wander through the galaxy, invisible until chance places them against the background of our telescopes? A fragment, a few hundred meters wide, is hard enough to detect. A nucleus several kilometers across, cloaked in its coma, challenges even our best instruments. For every one we catch, there may be countless others gliding through the dark, unknown, and unrecorded. In this way, Atlas is both a discovery and a warning. It tells us that the cosmos is more extravagant than our cautious models predicted. It reminds us that our knowledge is provisional, built not on certainties but on the limited sample of what we have seen. The threshold it reveals is not just about comet size, it is about the limits of our perception. We thought we knew the scale of interstellar debris. Now we realize the scale is larger, stranger, and perhaps only beginning to be understood. For the dreamer, this threshold is exhilarating. It suggests a galaxy alive with diversity, filled with travelers of every shape and size. For the scientist, it is humbling. It calls for new models, new surveys, and new questions about the distribution of matter in our galaxy. And for the rest of us, it is a reminder of the simple truth that keeps us gazing upward. The universe will always exceed our expectations, always find a way to reveal thresholds we did not know existed. Yet natural explanations remain powerful. Alien chemistry, ancient formation zones, and frozen CO2, rich ices, could all conspire to create this result. When faced with the unknown, the human mind often leaps toward the extraordinary. We imagine civilizations, technologies, and mysteries beyond comprehension. But just as often, the truth lies not in science fiction, but in science itself, subtle, elegant, and strange enough on its own. With Atlas, this perspective deserves careful attention. Perhaps we are not looking at something engineered, but rather at the astonishing extremes of nature's workshop. Consider the chemistry revealed by the James Webb Space Telescope. Its infrared gaze pierced the comet's hazy coma and found it unusually rich in carbon dioxide, far more so than in water. In comets of our solar system, water vapor is often dominant. But here, CO2 seems to carry the show. Such an imbalance hints at an origin in a colder, more remote environment than Earth has ever known. Perhaps a region of another solar system where carbon dioxide condensed in thick, glittering layers while water remained locked even deeper in ice. If this is the case, then Atlas may be a fossil from a distant planetary nursery, a frozen message preserved from a time and place utterly alien to our own. Its strange composition would then be not a mystery, but a signature, evidence of the diversity of star systems across the galaxy. One world grows comets filled with water, another grows them filled with carbon dioxide. Each carries the unique fingerprint of its home. The comet's mass, too, might be explained without invoking the extraordinary. Larger bodies are simply harder to fragment, harder to erode, harder to push off course. If Atlas began life as an oversized planetesimal, a building block that never quite grew into a planet, then its survival makes sense. It could have been ejected billions of years ago during a violent reshuffling of orbits in its parent system, wandering ever since, shielded by its sheer bulk from the attrition that grinds smaller objects to dust. Even its refusal to accelerate under outgassing can be framed as a natural outcome. What feels like defiance may simply be physics playing out on a grander scale than we are used to seeing. To hold to the case for nature is not to dismiss the allure of exotic ideas. It is instead to marvel at how remarkable the natural universe already is. The cosmos does not need help to surprise us. It produces comets that glow green with cyanide, asteroids that split themselves apart under sunlight, and planets that orbit so close to their stars they rain molten glass. Atlas may simply be the latest in this gallery of natural wonders, a reminder that reality is already stranger than our imagination often credits. And perhaps that is the deeper lesson. If nature alone can craft a comet this massive, this chemically unusual, and this stubborn against the forces that act upon it, then our galaxy is richer and more diverse than we dared assume. Sometimes, the natural explanation is not only sufficient, it is wondrous enough to keep us awake in awe, or lull us into sleep with dreams of distant worlds where comets like Atlas are born. JWST observations revealed a coma dominated by carbon dioxide. This composition hints at formation in a colder, more alien nursery than our own suns. When the James Webb Space Telescope turned its mirrors toward Atlas, astronomers expected to see the familiar signature of water vapor rising from its surface. Water, after all, is the dominant component in most comets of our solar system. But instead, the data told a different story, one in which carbon dioxide was not a minor player, but the star of the show. The discovery startled researchers. On Earth, carbon dioxide is an invisible, ever-present gas, part of our breath and our climate. In comets, it is usually present but not overwhelming, a companion to water rather than its replacement. For Atlas, the roles are reversed. Its coma glows with CO2 emissions, while water seems strangely muted. This imbalance suggests that the comet was forged in an environment where temperatures plunged so low that carbon dioxide could freeze in abundance. While water ice may have formed deeper below the surface, hidden from immediate release. Such conditions do not exist in our solar system today, at least not in familiar places. They point to a nursery far from the warmth of a parent star, perhaps at the icy outskirts of a protoplanetary disk, or even in a system orbiting a cooler, dimmer sun. To find carbon dioxide dominating a comet's chemistry is to read a message from a place fundamentally unlike our own, a frozen archive of alien weather and planetary birth. For astronomers, this evidence is more than a chemical curiosity. It is a reminder that comets are time capsules, preserving the conditions of their formation. Each volatile molecule is a page in a cosmic diary, telling us what was abundant, what was scarce, and what temperatures ruled the skies when the comet was born. In the case of Atlas, that diary describes a world colder and more exotic than the cradle of Earth. And yet, the questions only deepen. Why is the CO2 so dominant in the present coma? Has water sublimated away during eons of travel through interstellar space, leaving carbon dioxide as the survivor? Or was the comet always this way, a creature of an alien environment unlike anything our system has produced? The answers remain hidden, buried beneath layers of ice we cannot yet touch. Still, the significance is profound. The evidence of carbon dioxide sets Atlas apart, not just from our solar comets, but even from its interstellar predecessor, Borisov. It widens the spectrum of what comets can be, hinting that planetary systems across the galaxy forge icy bodies with extraordinary variety. In its chemistry, Atlas is both alien and familiar, a reminder that the elements we know so well on Earth can combine in ways that feel utterly foreign. As the comet continues its journey, its carbon dioxide trail lingers like a faint perfume across the solar system, a signature written in molecules. It tells us of a world we may never see, a star we may never visit, but whose story now flows invisibly through our own skies. To watch Atlas is to glimpse not only a comet, but the frozen breath of another sun's creation. If Atlas is heavier than expected, it may be preserving conditions from a stellar neighborhood older and harsher than our own. Astronomers often describe comets as time capsules. Locked within their ice, dust, and frozen gases are the fingerprints of the environments where they first formed. For most comets in our solar system, this means the Kuiper Belt or the Oort cloud, vast reservoirs of frozen debris where water ice, carbon monoxide, and organics can survive untouched for billions of years. But Atlas is no ordinary comet. With a mass estimated at 33 billion tons or more, it might hold not just a record of its birthplace, but of an entirely different era of galactic history. Picture a stellar nursery unlike our own. A region crowded with stars, their radiation harsh and unrelenting, their winds sweeping volatile gases into strange combinations. Here, giant planets may have stirred the disk with violent gravity, ejecting enormous fragments of rock and ice into interstellar space. Atlas, in this view, is a survivor of that chaos. Its size is not accidental but the result of collisions and mergers, building a nucleus so massive that it could withstand ejection and endure the long, cold journey between the stars. Its chemistry supports this idea. Observations with the James Webb Space Telescope reveal a coma dominated by carbon dioxide, a signature unlike the water-rich comets we know best. Such an abundance of CO2 suggests a nursery colder and more alien than the Sun's, where carbon dioxide could freeze in thick layers, while water ice remained buried or absent. If so, then Atlas is a message in chemical form, carrying the story of a stellar neighborhood we will never see directly. The implications ripple outward. If comets like Atlas are possible, then the galaxy is far more diverse than our current models suggest. Planetary systems may sculpt their debris in wildly different ways, producing not just fragile snowballs but interstellar mountains. Each one would be a frozen witness to the conditions of its home system, waiting silently until chance sends it drifting past a distant star. Skeptics caution restraint. The size estimates rely on assumptions about gas flow and dust production, and the uncertainties remain large. Yet even with those caveats, the possibility is profound. To imagine Atlas as a preserved fragment of an ancient neighborhood is to imagine holding a piece of galactic history in our telescopes. Its mass, its chemistry, its silence, all of these are pages in a story written billions of years ago. For us, that story is fleeting. Atlas will soon fade into the distance, continuing its journey through the Milky Way. But in its brief passage, it reminds us that the galaxy is not uniform. It is a mosaic of environments, each one leaving its mark on the comets it casts out. Atlas may be the first of its kind we have seen, but it will not be the last. And with each visitor, we add another piece to the great archive of the cosmos, an archive written not in words but in ice, dust, and the enduring weight of billions of tons. Harvard's claim is careful. They do not declare an exact size, only a lower bound, and that lower bound is already colossal. In science, certainty is a rare commodity. Observations are filtered through distance, noise, and the limitations of our instruments. The further we look into space, the more tentative our conclusions must become. With Atlas, the Harvard team chose a path of caution. Rather than proclaiming an exact diameter or an unshakable number, they focused on the minimum mass the comet must possess to explain its behavior. It is an art form in astronomy, setting limits rather than absolutes, boundaries rather than precise coordinates. This approach is rooted in humility. By admitting that much remains unknown, the scientists protect their conclusions from overreach. They cannot tell us whether the comet's nucleus is 5 kilometers wide or 15, but they can say with confidence that it cannot be smaller than a certain threshold without contradicting the observed data. In the case of Atlas, that threshold alone is staggering. Tens of billions of tons, a nucleus already vast enough to rival the most massive comets we have ever studied. Setting limits is often more powerful than it appears. A lower bound, by definition, says the truth is greater still. When a scientist declares that a comet is at least a certain size, they are hinting at possibilities that extend into realms uncharted. For Atlas, this means the reality could be even grander. The mountain in space even more immense than our cautious estimates suggest. The uncertainty itself becomes a source of wonder. And yet, the act of setting limits also invites debate. Critics point out that the boundary is only as good as the assumptions used to draw it. If gas outflow speeds differ from the estimates, if jets are misaligned or underestimated, then the lower bound could shift. This is the nature of scientific discourse. Each claim is tested, challenged, and reshaped through discussion. What remains remarkable is that even when stripped to its most conservative estimate, Atlas still emerges as something extraordinary. There is a quiet beauty in this restraint. In a world where headlines often chase absolutes, the Harvard team reminds us that truth often lies in ranges, in careful boundaries rather than bold declarations. To measure the immeasurable requires patience, and to accept uncertainty requires wisdom. For the dreamer listening, there is comfort in this as well. The comet itself does not change whether we measure it precisely or not. It drifts through space, indifferent to our debates, carrying with it the secrets of its origin. What matters is that even in our most cautious framing, it remains immense, a reminder of nature's capacity for scale. And perhaps that is the lesson hidden in the art of setting limits. Not every mystery yields its full truth. Some remain cloaked, offering us only glimpses. But even those glimpses are enough to expand our sense of what is possible. With Atlas, the lower bound is not just a number. It is an invitation to imagine what lies beyond it. In the uncharted territory where the true scale of the comet waits, still hidden in darkness. Estimating nucleus size through a cloud of glowing dust and gas is like measuring a candle hidden in fog. The answers are always slippery. When we look at comets, what our eyes or telescopes actually see is not the solid heart, but the veil surrounding it, the coma. This halo of vapor and dust, lit by sunlight, can stretch for hundreds of thousands of kilometers, dwarfing the tiny nucleus hidden at its core. The nucleus itself, the true comet, is only a fraction of what appears in our images. In the case of Atlas, that means the mountain-sized body, suspected by scientists, is buried deep beneath layers of radiance and haze. For astronomers, this poses a challenge as old as comet studies themselves. Light scatters in unpredictable ways through the coma. Dust particles glow differently depending on their size and composition. Gas emissions shift with the wavelength of observation. To disentangle the solid from the shining, scientists must build complex models, subtracting the glow of the coma in hopes of glimpsing the size of the hidden core. But no matter how carefully it is done, uncertainty lingers. In Atlas, the problem is magnified. Its coma is unusually active, dominated by carbon dioxide instead of water. This chemistry means the coma forms even further from the Sun, swelling larger and brighter long before the comet approaches close enough for traditional measurements. The nucleus, already difficult to isolate, becomes a phantom within its own brilliance. Each attempt to calculate its size must navigate the shimmering interference of its own vaporous shroud. This difficulty feeds into the debate. NASA's estimates, based on Hubble imagery, suggest a wide possible range, from less than half a kilometer to more than 5 kilometers in diameter. The Harvard team, by contrast, sidesteps the coma's confusion by relying on orbital mechanics, deducing mass from the absence of acceleration. Both approaches circle the same hidden truth, but from different angles, one through light, the other through motion. Each carries its uncertainties, and together they highlight the central problem. The coma conceals as much as it reveals. And yet, there is poetry in this concealment. The very feature that hides the nucleus is also what makes comets so enchanting. Without the coma, they would be dark rocks slipping silently through the sky. With it, they become luminous travelers, painting tales across the heavens, inspiring myths and awe for millennia. Their beauty is inseparable from their mystery. For Atlas, the problem of the coma may never be solved with certainty. But perhaps that is part of its gift. It reminds us that not every secret is meant to be fully unveiled, that sometimes the fog itself is part of the story. To measure a candle in fog is frustrating to science but soothing to the imagination. We know the flame exists, but its shape and size are softened, blurred, made dreamlike. In the same way, the nucleus of Atlas remains elusive, a mountain hidden behind a veil of starlight and gas, inviting us not only to calculate but to wonder. NASA places the nucleus between 440 meters and 5.6 kilometers, a wide gulf that leaves plenty of room for interpretation. This range, stretching from a modest hill to a mountain larger than some islands, reflects both the challenges of observing distant comets and the caution of scientific reporting. NASA's numbers are deliberately conservative, designed not to promise more than the data can safely support. By presenting such a broad span, they acknowledge both the limitations of our instruments and the complexity of Atlas's behavior. The lower end of the estimate, 440 meters, paints a picture of a nucleus no larger than a city block, still immense by human standards but relatively ordinary in cosmic terms. At that size, Atlas would be comparable to many known comets in our solar system, fragile, active, and easily influenced by outgassing. Yet the observed lack of measurable acceleration makes this possibility difficult to reconcile. How could something so small resist the push of its own jets? The physics seems uneasy with such modest dimensions. The upper bound, however, 5.6 kilometers, casts the comet in a very different light. A nucleus of this scale would rank among the largest interstellar objects ever studied. Its mass measured in tens of billions of tons. Such a body would glide with the stately inertia of a mountain, shrugging off the feeble thrust of escaping gases. This interpretation aligns more closely with the Harvard team's conclusions, though it still leaves questions about whether even 5.6 kilometers is enough to explain the comet's stubborn steadiness. Between these two extremes lies a vast zone of uncertainty, where each assumption about the coma, the gas flow, and the nucleus's reflectivity can nudge the estimate in one direction or another. NASA's choice to leave this zone uncollapsed is not indecision, it is discipline. Better to admit the limits of what can be known than to anchor claims to fragile numbers. In this cautious approach, there is a lesson about the nature of science itself. Certainty is rare, and humility is essential. To say, "we do not yet know," is not a failure, but an act of honesty that preserves trust. NASA's conservative estimates leave room for refinement, inviting future observations to sharpen the picture rather than pretending the picture is already clear. For the dreamer, though, this wide gulf opens space for imagination. Is Atlas a small wanderer masquerading as a giant, or is it truly a massive interstellar mountain cloaked in vapor? Each possibility carries its own story. The smaller comet would be a puzzle of balance, somehow arranging its jets so perfectly that they cancel out their thrust. The larger comet would be a tale of endurance, an alien iceberg so massive that the cosmos itself struggles to budge it. Both stories are compelling, and both remain alive within the data. As Atlas drifts onward, we may never pin down its exact dimensions. But perhaps that is the point. The range itself, the stretch from hundreds of meters to several kilometers, reminds us that the universe resists neat boundaries. In the twilight of uncertainty lies wonder, and in that wonder lies the quiet invitation to keep watching the skies. Loeb's team argues that even the largest of those estimates might not be enough. Their lower bound starts near NASA's ceiling. Where NASA's estimates tread cautiously, leaving a broad gulf of uncertainty, Harvard's approach presses firmly into the higher end of the scale. To Avi Loeb, Richard Cloaked, and Peter Verez, the numbers are clear. If Atlas truly resists its own outgassing with such stubborn indifference, then even 5 or 6 kilometers of nucleus may not suffice to explain it. Their calculations begin not at the bottom of NASA's range, but near its very top, and from there they build upward. This push beyond the range is rooted in a different kind of reasoning. Instead of relying on brightness and coma models, methods tangled in assumptions about reflectivity and dust, the Harvard team examines the comet's trajectory itself. They ask, how much mass is required to make the comet so unmoved by its own venting? The answer, in their equations, is staggering. To shrug off jets, measured in hundreds of kilograms per second, the comet must possess an inertia that borders on monumental. By starting near NASA's ceiling, the team implicitly casts doubt on the smaller values. A comet of only half a kilometer, they argue, would wobble noticeably under the same forces. Even a few kilometers in diameter might not provide sufficient heft. Instead, they lean toward a nucleus that could be considerably larger, perhaps exceeding the maximum size that Hubble's data can comfortably accommodate. The contrast between the two approaches NASA's wide caution and Harvard's confident push reflects not just differences in data, but differences in philosophy. One emphasizes restraint, leaving room for uncertainties. The other highlights the extraordinary, using absence of evidence as evidence of absence. Both perspectives are necessary, and both create tension within the scientific community. For supporters of Loeb's team, the argument is refreshing. It dares to treat the anomaly as real rather than as an illusion of measurement. It acknowledges the extraordinary scale implied and follows the numbers to their natural conclusion, however unsettling. To skeptics, however, the leap feels premature. They caution that assumptions about gas flow, vent orientation, and nuclear structure could all skew the result. A comet may be smaller and simply more cleverly balanced than we think. But even critics admit that Harvard's insistence cannot be brushed aside. By setting the lower bound so high, the team challenges other researchers to explain how such a massive appearance could be faked by smaller structures. It pushes the debate into sharper focus, forcing the community to weigh models carefully against the hard evidence of trajectory. For those of us listening in the quiet of the night, this scientific tug-of-war becomes part of the story's beauty. On one side stands the voice of caution. On the other, the voice of boldness. Between them lies the comet itself, gliding silently through the solar system, indifferent to both interpretations. Whether its nucleus is 6 kilometers wide or something even greater, Atlas continues to drift, vast and mysterious. A reminder that nature itself writes the final word, and it often writes beyond the ranges we expect. Some embrace the data, others caution restraint, reminding us that assumptions about outflow speeds and mass loss rates can skew the numbers. This division is nothing new in astronomy. Whenever the universe presents us with something unfamiliar, the community splits into camps of bold interpretation and careful skepticism. Atlas is no exception. On one side are those who see in its immense inertia the unmistakable signature of mass far beyond prior expectations. On the other side are those who urge patience, pointing out that every calculation is built atop a pyramid of assumptions that could shift if even one parameter is wrong. The crux of the debate lies in the invisible forces acting within the comet's coma. We cannot measure the exact speed of every molecule vented from its nucleus. We cannot map every fissure or crack where gas escapes. Instead, astronomers must approximate. They assume average speeds, average pressures, and uniform activity. From these assumptions, equations are built, and from those equations, conclusions arise. If the assumptions wobble, so too does the conclusion. Supporters of Harvard's interpretation argue that the data are too consistent to dismiss. The comet has been tracked over months, and its trajectory has remained faithful to gravity's pull. If outgassing were significant, it should have revealed itself by now. The absence of measurable deviation, they say, is not an illusion but a fact that only a massive nucleus can explain. Skeptics counter with alternative possibilities. What if the jets are aligned in such a way that they cancel one another, producing little net thrust? What if the outflow speeds are lower than assumed, reducing the force they exert? What if the surface activity is patchy, inconsistent, or concentrated in regions we cannot yet see? Each of these possibilities would lower the required mass, bringing the comet's size back within the comfortable bounds of known physics. This tension between boldness and caution is the heartbeat of science. It is a dialogue that plays out in papers, conferences, and quiet debates over datasets. One side pushes the frontier outward, daring to imagine that the comet is larger, stranger, perhaps even anomalous. The other side pulls back, reminding us that extraordinary claims require extraordinary evidence. Both are necessary, for it is in their friction that progress is made. For listeners drifting into sleep, the divide itself becomes a kind of lullaby. Science is not a chorus singing in unison, but a symphony of competing instruments, some loud, some soft, weaving discord into harmony. The disagreements are not failures, they are the very fabric of discovery. And so, astronomers remain divided. Some see in Atlas the weight of a new category of interstellar giants. Others see the mirage of uncertain assumptions, a puzzle that may dissolve with better data. The comet itself, silent and immense, offers no clarification. It continues on its path, indifferent to our debates, a reminder that truth often drifts ahead of certainty, waiting for us to catch up. The first interstellar visitor split the community. Artificial hypotheses drew headlines. Will Atlas reopen that same rift? When Oumuamua flashed through our solar system in 2017, it arrived as both a gift and a challenge. Its elongated shape, unusual brightness, and puzzling acceleration defied easy explanation. Some researchers lean toward natural causes. Fragmentation of a larger body, perhaps, or outgassing too subtle for our instruments to see. But others, most famously Avi Loeb, suggested that the odd behavior might point to something more extraordinary, an artificial object, perhaps a probe or a fragment of alien technology. The suggestion captivated the public and fractured the scientific community. The debate around Oumuamua was more than a dispute over data. It became a mirror for how we handle the unknown. One camp embraced conservative explanations, reluctant to invoke extraordinary claims without extraordinary proof. Another camp pushed the boundaries, asking whether clinging too tightly to the familiar blinds pushes us to possibilities that lie just beyond our comfort zone. The result was a rift that lingers even today, a fault line between bold imagination and cautious skepticism. Now comes Atlas, and with it, echoes of that earlier debate. This time, the anomaly is not a strange acceleration but a lack of it. The comet vents gas into space yet does not deviate from its gravitational course. To some, the explanation is simple. Its mass is enormous. To others, the question lingers, could there be another reason? If Oumuamua stirred talk of technology, will Atlas do the same? The parallels are striking. Both objects arrived from interstellar space, carrying mysteries encoded in their motion. Both revealed behaviors that stretched our understanding of comets and asteroids. And both drew Avi Loeb into the spotlight, challenging the boundaries of mainstream interpretation. Yet, there are differences too. Where Oumuamua left little physical evidence, no coma, no tail, Atlas offers abundance: jets, dust, chemistry, and light. It is less elusive, more measurable. And yet, even here, the data resists certainty. The lesson of Oumuamua is not that the bold were wrong or the cautious were right. It is that science thrives on the tension between them. Debate fuels inquiry. Disagreement sharpens models. And public fascination, even when sparked by the most speculative ideas, can inspire the next generation of observers and thinkers. As we consider Atlas, we are wiser now than we were in 2017. We know how easily the unknown can polarize. We know that mysteries invite not only answers but narratives. The challenge is to balance them, to hold wonder in one hand and discipline in the other. So, will Atlas reopen the rift? Perhaps. But perhaps that is not something to fear. Perhaps the debates themselves are part of the process, guiding us closer to truth. As the comet sails on, silent and immense, it reminds us that the cosmos does not conform to our arguments. It is vast enough to contain both caution and imagination, both skepticism and awe. And in its silence it teaches us again the most important lesson of all: that discovery is rarely unanimous, but always worth the journey. Here lies the central paradox: plenty of gas escapes, yet the object does not move. Something must give. The paradox is stark. When sunlight warms a comet, it awakens the ices within, releasing carbon dioxide, carbon monoxide, and water into the vacuum. The force of this escaping gas, though faint compared to rockets we build on Earth, is usually enough to alter a comet's motion ever so slightly. Over days and weeks, astronomers track those changes, noting the gentle curves in its path, the slight adjustments caused by this invisible propulsion. Yet Atlas refuses to play by the rules. The gas is there, The coma expands, the tails stream behind it, and still its orbit remains untouched. It is as if we were watching a kettle boil furiously, yet the steam failed to push against the air. A process we understand deeply behaves in a way that seems impossible. The Harvard team took this absence seriously, treating it not as a mistake in observation but as a clue. If the jets cannot move the comet, then the comet must be too massive for them to matter. Like a mountain resisting the breath of the wind, it glides forward, unmoved by its own activity. But is that the only answer? Here lies the heart of the debate. Perhaps the gas vents are arranged in such a way that their forces cancel. A jet on one side could be matched by a jet on the other, leaving no net thrust. Or perhaps the outflow speed is lower than expected, meaning the force is weaker than our models predict. These possibilities are not impossible, yet the longer Atlas is observed, the harder they are to sustain. Symmetry that perfect would be rare, low outflow speeds that consistent would be unusual. Still, nature has a way of surprising us. Dust grains can clog vents, reshaping flows. Thermal layers can alter sublimation, producing uneven activity across the surface. To dismiss these options too quickly would be unwise. And so the paradox remains suspended between two worlds, one where mass explains the silence, and one where complexity hides the motion. For astronomers, the paradox is not merely a frustration but an opportunity. Every anomaly is a window, a chance to refine our models, to ask questions we did not know to ask. Why does Atlas vent so much carbon dioxide instead of water? Why does its coma grow so vast without disturbing its path? Each question pushes us toward deeper understanding, not just of this one comet, but of the hidden mechanics of all icy wanderers. And for those listening tonight, the paradox is a gentle reminder of the universe's ability to hold contradictions. It shows us that silence can coexist with motion, that stillness can exist amid activity. A comet can breathe without moving, just as we can dream without stirring. Outgassing without acceleration may puzzle the scientist, but to the dreamer, it is poetry. It is a paradox written in starlight, a quiet song sung by a mountain of ice as it drifts through the solar system. Something must give, yes. But perhaps what gives is not the comet's path, but our assumptions about what is possible. Imagine a stone so large that no breath of wind could shift it. That is the image Harvard paints of Atlas. For most comets, the sublimation of ice is enough to act like a set of thrusters, nudging their paths gently off course. These tiny but persistent forces accumulate, gradually altering trajectories in ways that can be measured and predicted. Yet in the case of Atlas, those same forces appear to vanish into insignificance. The comet continues along its orbit, as though the gas jets do not exist. To account for this, Loeb and his colleagues propose the simplest explanation. The comet is simply too massive to be moved. This is the essence of the too heavy to push hypothesis. The gases are there, streaming outward in clouds of carbon dioxide and dust. They exert pressure, just as physics dictates they must. But the nucleus is so large, so packed with mass, that the effect is swallowed whole. The thrust exists, but it cannot compete with the inertia of a body measured in tens of billions of tons. Picture standing beside a mountain and blowing against its side with all your strength. The wind may ruffle the grasses, scatter dust, even carry your breath far across the slopes, but the mountain itself does not move. In the same way, the sun's warmth awakens Atlas, stirring activity on its surface, but its bulk makes such forces irrelevant. Gravity alone holds sway, pulling it forward on a steady, unbroken line. Critics note that this hypothesis leans heavily on assumptions. If the gas is venting unevenly, or at slower speeds than expected, then the absence of acceleration could be explained without invoking enormous mass. But Harvard's team argues that such coincidences are unlikely to persist for months on end, across countless rotations and exposures to sunlight. The more natural explanation, they suggest, is simply that the comet's nucleus is extraordinarily large. This view, if correct, places Atlas among the most massive interstellar bodies ever observed. It also challenges our models of what kinds of debris planetary systems can produce and eject. How common are such giants? How often do star systems fling away objects measured not in hundreds of meters, but in kilometers? If Atlas is not unique, then the galaxy may be filled with hidden mountains drifting silently between the stars. For astronomers, the too heavy to push hypothesis is both unsettling and inspiring. It demands we expand our models of comet formation, and it reminds us that nature often exceeds the boundaries we set. For dreamers, it offers a powerful image. A cosmic mountain gliding through the void, unmoved by its own breath, carried only by the gravity of the stars it passes. In this stillness lies a kind of poetry. Atlas becomes not just a comet, but a metaphor for endurance. Vast, immovable, serene. It is a reminder that in the grand theatre of the cosmos, some players move lightly, buffeted by every force, while others, like this interstellar giant, drift on untouched, too heavy to be pushed, too massive to be swayed. Could an object be built deliberately to be this massive, to mask its acceleration, to appear as nothing more than a comet? It is a question that tiptoes on the border between science and speculation, one that captures the imagination even as it stirs skepticism. The notion of exotic engineering suggests that what we see as natural might instead be intentional. If an advanced civilization wished to disguise a spacecraft, could they cloak it in ice and dust, shaping it into the image of an ordinary comet? Could the vast weight of Atlas be a design choice? A way to prevent any small acceleration from revealing its true nature? This line of thought is not new. Ever since Oumuamua sparked discussions about artificial origins, astronomers and dreamers alike have considered whether some interstellar objects might be more than they seem. In the case of Atlas, the idea gains traction from its sheer scale. A nucleus so large that outgassing fails to shift it, such resilience could, in theory, be engineered. A heavy core of exotic materials, wrapped in volatile ices, would produce the outward appearance of a comet while concealing advanced technology within. But as seductive as the theory sounds, it comes with challenges. Engineering such an object would demand resources on a scale far beyond anything we can currently imagine. Billions of tons of material would need to be shaped, accelerated, and launched into interstellar space. To us, the idea feels almost impossible. Yet when contemplating civilizations millions of years older than ours, it is dangerous to dismiss what might be within their reach. Supporters of the idea often point to the strategic advantage of such a disguise. A probe hidden in the form of a comet would blend seamlessly into the background of the galaxy. To casual observers, it would look like nothing more than a natural wanderer, its gas jets and coma masking any signals within. Only by studying its motion carefully and noticing the absence of acceleration might we suspect something unusual. Skeptics, however, remind us that extraordinary claims demand extraordinary evidence. So far, no such evidence has emerged. Every observation of Atlas can still be explained within the framework of natural processes, volatile chemistry, immense size, or unusual outflow dynamics. To leap to artificial explanations too quickly risks overshadowing the extraordinary reality of nature itself. And yet, the allure persists. To imagine a hidden engine within, a craft cloaked in ice, is to flirt with the boundaries of possibility. Even if unlikely, such theories spark curiosity, drawing public attention and inspiring new generations of scientists to look deeper, to question more boldly. In that way, the idea of exotic engineering serves a purpose. It keeps the imagination alive, reminding us that the unknown is fertile ground for wonder. Whether Atlas is a comet forged by nature or something more deliberate, it glides through our skies indifferent to our theories. For now, it is enough to marvel at the mystery, to dream of possibilities, and to remember that sometimes the most exotic engineering belongs not to civilizations, but to the universe itself. Science demands evidence, and while speculation may attract curiosity, extraordinary claims remain unproven. without extraordinary proof. This principle, often repeated in scientific circles, serves as a guiding light whenever the unknown tempts us with possibilities. A comet behaving strangely, a trajectory defying expectations, a chemistry that seems unusual. Each of these sparks wonder, but none by itself is proof of something extraordinary. With Atlas, we find ourselves at this familiar crossroads. Natural explanations abound, yet whispers of exotic theories linger in the air. The burden of proof reminds us not to confuse curiosity with confirmation. In practice, this means that even the most dramatic hypotheses must be held to the same rigorous standards as ordinary ones. If someone proposes that Atlas is artificial, the evidence must exceed what would be required to show it is a natural comet. Such claims must withstand not only scrutiny, but skepticism, offering testable predictions and measurable phenomena that can be independently verified. Without this, speculation remains just that, a story told in the absence of certainty. Astronomy, more than many sciences, teaches humility in this regard. The objects we study are distant, faint, and often glimpsed only briefly as they pass through the reach of our instruments. Every number is an estimate, every conclusion a probability. Against this backdrop, it is easy to mistake anomalies for revelations. A missing acceleration may suggest immense mass, but it could also reflect hidden complexities in venting. A strange chemistry may feel alien, but it could be the fingerprint of a natural nursery far from the sun. The burden of proof is not meant to stifle imagination. Rather, it is meant to protect us from the eagerness of our own minds. Humans are natural storytellers. When faced with mystery, we weave narratives, some cautious, some bold. Science honors those narratives but insists that they be tethered to evidence. This discipline is what separates wonder from truth. And yet, speculation still plays a vital role. It keeps questions alive, ensuring that the conversation does not end with the first explanation offered. Without it, science would stagnate. The key is balance, embracing the spark of curiosity while keeping one's feet grounded in data. When handled this way, even extraordinary claims contribute meaningfully, not as conclusions but as provocations that drive deeper study. For Atlas, the extraordinary claim that it may be something other than natural remains unproven. What we have are hints, absences, and unusual behavior, all of which can still be explained through the lens of natural physics. Until evidence emerges that cannot be reconciled with such explanations, the comet must remain a natural wonder, remarkable enough without adornment. And in truth, is that not enough? A mountain of ice and rock from another star system, drifting into our skies, is already extraordinary. Its chemistry, its mass, its endurance across interstellar gulfs, all of these speak of a universe vast and varied, a universe that crafts wonders without assistance. The burden of extraordinary claims reminds us to treasure this reality, to let nature's artistry stand on its own, and to wait patiently for the day when evidence, not speculation, carries us further still. If many Atlas-sized bodies exist, where did they come from? The galaxy would be littered with more debris than models allow. Astronomers have long tried to calculate how much material star systems fling into interstellar space. As planets form, their gravitational interactions act like cosmic slingshots, hurling comets and asteroids outward until they escape their parent star entirely. Over billions of years, this process fills the galaxy with wandering fragments, pebbles, boulders, icy shards, and sometimes objects hundreds of meters across. But the numbers, as our models suggest, should not favor mountains. Small fragments are far more common. If Atlas represents a larger class of interstellar debris, then our understanding of how planetary systems evolve may be incomplete. The problem is one of scale. A comet nucleus, several kilometers wide, is not just a rock. It is a monument, requiring a tremendous reservoir of raw material to form. For a star system to eject many such bodies, it must not only forge them in the chaos of planetary birth, but also have enough gravitational violence to fling them free. Models of planetary dynamics predict this can happen, but not in such abundance that the Milky Way should be crowded with giant wanderers. And yet, here Atlas is, whispering that perhaps those models underestimate the true population. If these massive bodies are common, they raise practical questions as well. How often do such giants pass near Earth without being seen? Our telescopes are improving, but detection is biased toward objects that glow brightly or happen to align with our surveys. A dark, mountain-sized nucleus with little activity could slip past unnoticed. Atlas, by displaying a bright coma, revealed itself. The population problem also stirs broader implications. If interstellar space teems with these giants, then the total mass of debris drifting between stars is immense, far greater than expected. This would reshape our understanding of galactic structure. It might even play a role in seeding young systems with raw material. Imagine a giant comet plunging into a forming disk, donating its volatiles, stirring its chemistry, or colliding with an infant planet. The galaxy could be far more interconnected than we thought, with comets acting as messengers and gardeners on a cosmic scale. But if Atlas is rare, then its arrival in our time is remarkable, a stroke of cosmic luck that places us as witnesses to something few civilizations may ever see. This interpretation solves the population problem, but leaves us with another. Why here? Why now? Coincidence is possible, but the mind resists it. Astronomers continue to wrestle with the paradox. Either the galaxy is filled with unseen mountains, or Atlas is a rare jewel hurled into our skies against all odds. Both options expand the mystery. Both suggest that our models of planetary formation, while useful, are only sketches of a deeper truth. And so the population problem lingers, unresolved. To solve it, we will need more visitors, more data, more nights spent watching the dark sky for a glimpse of another wandering giant. Until then, Atlas stands alone, a reminder that even a single discovery can challenge the architecture of our understanding, forcing us to redraw the galaxy in our minds. Such objects require vast amounts of material. Their existence challenges how much planetary debris galaxies can realistically eject. Every comet, every asteroid, every wandering fragment of interstellar space carries within it the story of its origin. For smaller bodies, the explanation is simple enough. Planetary systems are messy places, and countless small shards are flung outward during the dance of planet formation. But when we confront a body as immense as Atlas, the numbers become difficult to reconcile. To forge something so massive, and then to eject it into interstellar exile, requires not only extraordinary violence but also extraordinary abundance of raw material. Here lies the mass budget crisis. The galaxy contains a finite amount of matter, distributed among stars, planets, and the drifting debris between them. If bodies the size of Atlas are common, then planetary systems must be throwing away far more mass than current models suggest. The arithmetic does not quite add up. We would have to imagine worlds birthing giants, only to hurl them into the void in staggering numbers, a wastefulness that stretches credibility. Planetary dynamics can, in theory, eject large bodies. Gas giants tug comets into new orbits, slingshotting some to freedom. Close encounters between massive planets and icy planetesimals can catapult them beyond the reach of their star. But such events are rare compared to the steady trickle of smaller debris, and rarity alone may not explain Atlas. If just one giant comet like this passes through our neighborhood in a matter of decades, the implication is troubling. Perhaps there are far more out there than we can comfortably explain. The crisis deepens when we think in terms of scale. A nucleus several kilometers wide contains billions of tons of material. If even a fraction of planetary systems eject objects this large, the interstellar medium should be thick with them. Yet our telescopes, sensitive as they are, have only found a handful. Either our models underestimate their abundance, or we have been extraordinarily lucky or unlucky in spotting such a giant so soon. This dilemma forces astronomers to revisit their assumptions. Perhaps the early stages of planet formation are even more chaotic than we believe. producing surplus giants that are doomed to wander. Or perhaps Atlas is not typical at all, but a statistical outlier, a rare product of unusual conditions. Both explanations come with consequences. Either we must expand the galactic mass budget, or we must accept that our sample so far is misleading. For the dreamer, the phrase mass budget crisis takes on a poetic quality. It is not just a problem of numbers, but a reminder of how delicately we balance what we know against what we do not. The galaxy, in all its immensity, resists being neatly accounted for. It will always spend more mass, more energy, more wonder than our ledgers predict. Atlas, with its colossal bulk, stands as a challenge written across the sky. Until we have more answers, it remains a question heavy with mystery, a weight pressing against both our models and our imagination. Perhaps our models are wrong. Perhaps star systems can eject more giants than we thought possible. For decades, astronomers have relied on simulations to estimate how planetary systems behave in their youth. These models show new planets forming amid swirling disks of gas and dust, colliding and migrating, scattering debris into chaotic trajectories. Many of those fragments are pulled inward and destroyed, while others are cast outward into cold exile, eventually breaking free into interstellar space. The consensus has been that most of what escapes are small, icy shards, fragile comets, rocky splinters. But if Atlas is as massive as Harvard's team suggests, then perhaps we must broaden our view of what planetary systems are capable of ejecting. The logic is simple. If we have already seen several interstellar visitors in just a few years of close observation, and one of them appears to be a giant, then large-scale ejections may be more common than previously believed. Our simulations might underestimate the violence of early planetary migrations or the sheer number of planetesimals formed in the first place. Young star systems may not merely sprinkle small debris into the galaxy. They may hurl out mountains. This possibility forces us to imagine planetary nurseries in a new light. Consider a system where gas giants migrate inward and outward, sweeping through the disk like titans. Their gravitational pulls would scatter planetesimals far and wide, with some collisions shattering them into fragments and others sending intact giants into the deep. Perhaps Atlas is one such survivor, a body that narrowly escaped accretion into a planet and instead was exiled from its birthplace. If so, then our galaxy may be richer in massive wanderers than we realized. For every Atlas we see, countless others could be passing unseen, dark against the void, never aligning with our telescopes. The idea is staggering. An invisible population of cosmic mountains drifting through the Milky Way, reminders of the chaos from which planets emerge. Of course, rethinking models also means facing uncertainties. How efficient must a planetary system be to eject so many giants without depleting itself? Would such systems still produce stable planets, or would the violence of so much scattering prevent habitable worlds from forming? If Atlas represents the norm rather than the exception, then the story of planet formation is even messier and more extravagant than our simulations have shown. Critics argue that it is premature to overhaul models based on a single object. Yet history reminds us that anomalies often carry truths. When one data point defies expectations, it plants a seed of doubt, and sometimes that seed grows into a revolution of thought. In the quiet of night, the notion feels both unsettling and wondrous. Perhaps star systems do not merely shape themselves with care, but with chaos and abundance. Perhaps the galaxy is littered with giants because nature does not build sparingly. It builds extravagantly, scattering mountains into the dark as casually as pebbles. If so, then Atlas is not an exception, but a messenger, inviting us to rethink what planetary systems can truly create. Alternatively, Atlas might be an outlier, a once-in-a-billion object that just happened to pass through our neighborhood. Astronomy often teaches us humility through rarity. Some phenomena are so uncommon that entire generations pass without witnessing them. Supernovae blaze in distant galaxies more often than they do in our own. Collisions between stars, the births of black holes, or the merging of neutron stars all occur, but so infrequently nearby that they feel like miracles when they happen in view. Perhaps Atlas belongs to this category. Not a member of a vast hidden population, but a singular event, rare beyond reckoning, that wandered into our skies by chance. If this is true, then the discovery is no less extraordinary. For a once-in-a-billion object to appear now, in the short span of human observation, would make our timing remarkable. We have only had the technology to detect such faint visitors for a few decades, yet already we have seen 3: Oumuamua, Borisov, and now Atlas. The odds, if Atlas is truly that rare, border on the incredible. And yet, coincidences do happen. Nature, vast and indifferent, does not arrange its schedule around human readiness. Sometimes the improbable aligns with our gaze. The rarer-than-rare interpretation offers one advantage. It preserves our existing models. If planetary systems cannot easily eject objects of this scale, then Atlas must simply be an exception. Perhaps it formed under unusual conditions, an oversized fragment from a massive collision, or a survivor of a uniquely chaotic system. Its journey across the galaxy may have taken billions of years, wandering endlessly until it intersected with our solar system. Yet this explanation, while tidy, leaves us with an uneasy feeling. If Atlas is so rare, why did we encounter it so quickly after detecting our first interstellar visitor? Why not centuries from now, or never at all? Are we to believe that chance aligned in our favor so perfectly? For some scientists, this level of coincidence feels unsatisfying, even if it remains logically possible. But rarity is part of the universe's character. The night sky itself is a tapestry of rare alignments: eclipses, meteor showers, planetary conjunctions. Each one feels improbable, until we remember that time is vast, and given enough of it, even the rarest of events becomes inevitable. Perhaps Atlas is the same. An unlikely traveler whose timing is not miraculous, but simply the inevitable outcome of billions of years of motion. To think of Atlas as rarer than rare is to see it as a gift. A comet not representative of a hidden population, but a singular messenger, offering us a glimpse of what is possible even if never repeated. It suggests that the universe still holds surprises that defy our statistics. Phenomena so unusual that they remind us of how much we do not yet know. Whether common or rare, Atlas carries the same lesson. The cosmos will not always conform to our expectations. It will, from time to time, place something before us that feels improbable, even impossible. And in those moments, the universe whispers that rarity itself is part of the wonder, that sometimes, to see the rarest of the rare, all we must do is look up. For scientists and dreamers alike, the allure lies not in certainty, but in the shadows between. Certainty brings closure, but mystery keeps us watching the skies. With Atlas, much remains unresolved: the size of its nucleus, the true nature of its chemistry, the exact reason for its unshakable orbit. Each uncertainty is not merely a gap in knowledge, but an invitation. For the scientist, it is an open question that demands data, models, and patient refinement. For the dreamer, it is a doorway to wonder, a chance to imagine possibilities that stretch beyond the boundaries of current understanding. This duality has always defined humanity's relationship with the cosmos. When ancient peoples saw comets blazing across the heavens, they did not know about sublimating ices or orbital mechanics. They filled the void with myth, with gods and omens, with stories that gave shape to the unknown. Today, we trade mythology for mathematics. Yet the pull of mystery remains. A comet like Atlas whispers in much the same way, reminding us that knowledge and wonder are not opposites, but partners. The seduction of the unknown lies in its balance. Enough evidence to intrigue, but enough absence to leave room for imagination. We know Atlas is real, we see its coma, track its path, measure its spectrum, but we do not know its exact size, nor its origin, nor its destiny. In this twilight between fact and speculation, possibilities bloom. Perhaps it is simply a massive comet born in a distant nursery, or perhaps it is something more, an outlier, a messenger, even a construct of unimaginable design. The lack of certainty keeps every option alive, at least for now. Scientists, of course, must lean toward restraint. They build models that explain what is observed without reaching beyond the data, yet even they are not immune to the pull of mystery. The most rigorous researcher still feels the thrill of facing something unresolved, something that stretches the boundaries of what is known. This thrill is not a distraction from science, it is the spark that drives it forward. For dreamers and storytellers, the unknown is a canvas. Atlas becomes whatever imagination paints upon it. A cosmic mountain adrift in space, a relic of a shattered world, a disguised probe, a time capsule from another star. None of these visions need to be true for them to have value. They remind us that we live in a universe where even small glimpses can ignite vast possibilities. And so the seduction of the unknown continues. Each night Atlas glides through the void. We are reminded that certainty is not the only treasure the cosmos offers. The shadows themselves hold meaning. They invite us to lean closer, to look again, to wonder. And in that wondering lies something deeper than knowledge. The feeling of being part of a universe, vast enough to always keep secrets, vast enough to always leave us curious. In the end, certainty may close the book on Atlas. But until that day comes, the unknown itself is the story, soft, open-ended, and endlessly compelling. ESA and NASA probes near Mars are watching. Their data may confirm or challenge Harvard's conclusions. In the vastness of space, comets often pass unnoticed, but Atlas has attracted the watchful gaze of instruments beyond Earth. As the comet threads its way through the inner solar system, its path brings it close enough to Mars that orbiters and landers can catch a glimpse. These spacecraft, built for other purposes, now find themselves witnesses to an interstellar visitor, their instruments tuned to track faint signals of dust, gas, and motion. For scientists, this moment is precious. Earth-based telescopes, powerful as they are, suffer from distance and distortion. Light must pass through our atmosphere, blurring signals and filtering out detail. From Mars, however, the view is different, clearer, crisper, and closer. Probes circling the red planet can measure the coma with greater sensitivity, record its chemistry with more precision, and perhaps even detect subtle changes in the comet's trajectory that Earth-bound instruments might miss. The hope is that this independent vantage point will sharpen the debate. Harvard's claim, that Atlas is more massive than expected, rests heavily on the absence of detectable acceleration. If Mars-based probes can confirm this absence, the case strengthens. If, however, they find small deviations invisible from Earth, the comet's size may shrink back into a more ordinary range. Either outcome would refine the truth. Among the instruments tasked with this quiet surveillance are spectrometers designed to study planetary atmospheres. They can break the light of the coma into its component wavelengths, revealing the fingerprints of carbon dioxide, water, and dust. High-resolution cameras, too, may glimpse structures in the tails, jets that spray in directions we cannot easily see from Earth. Each faint image, each line of data, becomes a piece of the puzzle. And then there is the possibility of serendipity. A probe might detect unexpected dust grains brushing past, or record changes in the plasma environment as Atlas's gases interact with the solar wind. Such chance encounters could reveal properties of the comet invisible from afar, offering new clues about its true mass and nature. The presence of Mars as a secondary observer also speaks to the collaborative nature of exploration. Earth and Mars, separated by millions of kilometers, now work together as two eyes on the same mystery. What one cannot see clearly, the other may resolve. It is a reminder that science is not just about instruments, but about perspectives, angles of view that, when combined, bring sharper focus to the unknown. For the dreamer, this moment holds quiet poetry. Imagine probes built to study a red desert world, suddenly lifting their gaze to watch a visitor from the stars. Imagine the data streaming back, carrying whispers of an interstellar mountain drifting silently past Mars. Whether the numbers confirm Harvard's bold claims or temper them, the act of watching itself is profound. As Atlas moves on, leaving Mars behind, the memory of those flybys will remain, a testament to how even distant outposts of human technology can join in the cosmic conversation, listening carefully as the universe tells its story. The James Webb Space Telescope has already transformed the debate, offering a spectrum that reveals chemistry invisible to the eye. Unlike visible light telescopes, which show us only the glow of dust and gas, JWST peers into the infrared, where molecules leave their fingerprints in delicate absorption lines. When astronomers turned Webb's golden mirrors toward Atlas, they saw not just a comet's shimmering halo, but the precise story of its chemistry. Carbon dioxide dominated the spectrum, far outshining the expected water lines. Methane, carbon monoxide, and traces of other volatiles flickered faintly as well, each adding nuance to the comet's portrait. This discovery shifted the conversation dramatically. For decades, we have studied comets in our own solar system, and most conform to a familiar pattern: water ice as the primary driver of activity, with carbon dioxide and carbon monoxide playing secondary roles. Atlas, however, is different. The CO2 lines are so strong that they reshape our sense of what a comet can be. Such chemistry hints at a birthplace colder, darker, and more remote than our sun's nursery. A region where carbon dioxide froze freely, while water remained buried or inert. JWST's role as a silent witness is especially poignant. The telescope does not speak in images that dazzle the casual eye. Instead, it whispers in spectra, patterns of light that require interpretation. To the untrained observer, the data may look like nothing more than jagged lines on a graph. But to scientists, those lines are revelations. They tell us not only what the comet is made of, but also where it may have formed, how it has survived, and why it behaves so differently from comets we know. And yet, Webb's observations also raise questions. If carbon dioxide dominates Atlas's activity, why is there so little measurable acceleration from its jets? Are the gases venting more gently than we think? Or is the comet's nucleus so massive that even such vigorous activity cannot alter its course? Here again, chemistry and dynamics collide, with Webb's data feeding into the broader debate over size and mass. The telescope also highlights the power of collaboration. Ground-based observatories can track Atlas's orbit with exquisite precision. Hubble can capture its coma in stunning visible detail. Mars probes can provide a second vantage point. But it is Webb, stationed 1 million miles from Earth, that can tell us what the comet is made of. Each perspective complements the other, weaving together a fuller picture of a visitor that refuses to be simple. For listeners drifting into sleep, there is something deeply calming about this image. A great golden eye, suspended in the cold of space, silently gathering the faintest signals of light, unraveling mysteries from across the galaxy. JWST does not judge, does not speculate. It observes, patiently, faithfully, revealing truths invisible to human senses. And as Atlas continues its passage, Webb will continue to watch, recording the molecular whispers of a world that has travelled for billions of years to reach us. In its silence lies clarity, and in its spectra lies the poetry of science, light transformed into knowledge, knowledge transformed into wonder. Why so much carbon dioxide? Why so little water vapour? These ratios are far beyond ordinary. For comets in our own solar system, water is usually the dominant voice. As they near the sun, frozen water awakens first, flooding the coma with vapour that carries dust into a luminous veil. Carbon dioxide is present too, but secondary, often measured in modest amounts compared to water. Yet Atlas refuses this familiar script. Its spectrum shows carbon dioxide as the lead actor, with water playing at best a supporting role, or perhaps hiding entirely, buried too deep to reveal itself. This imbalance has puzzled astronomers since the first JWST observations. Why should carbon dioxide dominate so thoroughly? One explanation is birthplace. If Atlas formed in the farthest reaches of a cold protoplanetary disk, temperatures may have dropped low enough for carbon dioxide to condense in great abundance. Water, by contrast, might have remained frozen in deeper layers, or even absent from the comet's formation zone. In such an environment, CO2 would naturally become the driving force behind its later activity. Another possibility is survival. As Atlas drifted through interstellar space for millions, perhaps billions, of years, its surface layers may have been eroded by cosmic radiation. Water ice, being more volatile, might have sublimated away long ago, leaving behind carbon dioxide as the dominant survivor. What we see today could be the weathered remnant of an ancient body, stripped of its original balance, altered by eons of exposure to the galaxy's silent storms. Yet there are more complex scenarios. Perhaps the comet's nucleus is stratified, layered like the rings of a tree. As one layer sublimates, another emerges. If Atlas is still venting its outer carbon dioxide shell, the water-rich interior may remain locked away, waiting for a future epoch of its journey. What we witness now could be only one stage of a slow unveiling, a chemistry that shifts with time and distance. The mystery deepens when we compare Atlas with its predecessors. Oumuamua showed no detectable coma at all, leaving us grasping for explanations. Borisov looked comfortably familiar, dominated by water like our own comets. Atlas, however, belongs to neither category. It straddles a new space, active, but alien in its ratios, forcing us to admit that interstellar comets are not variations on a theme, but entirely new compositions. For astronomers, the CO2 mystery is not just about chemistry, it is about what kind of systems populate the galaxy. If Atlas is rich in carbon dioxide, what does that say about the star it once orbited, or the disk from which it emerged? Could there be planetary systems where water is scarce and carbon dioxide shapes the story of worlds? If so, then our own solar system with its water-driven comets may be less typical than we imagined. For listeners, the riddle is soothing in its uncertainty. A comet drifting silently through space, exhaling not water but carbon dioxide, becomes a symbol of the cosmos's ability to surprise. It reminds us that even familiar elements can combine in alien ways, painting pictures of worlds we will never see. The ratios may defy our expectations, but in that defiance lies wonder, the kind that keeps us watching, questioning, and dreaming beneath the stars. If Atlas grew in a different stellar nursery, its very chemistry is a message from another sun. Every comet carries the story of its birth. Within its ices and dust lies a record of the temperatures, pressures, and ingredients that shaped it billions of years ago. For comets in our solar system, that story is one we know well. Water ice mixed with silicates and organics, forged in the outer regions beyond Neptune where the cold preserved them. But Atlas seems to tell a different tale. Its carbon dioxide dominance, its unusual behavior, and its stubborn refusal to accelerate all point toward a nursery unlike our own. Imagine a young star system forming light years away, its disk swirling with frozen gases and rocky debris. Around that distant sun, conditions may have been colder or more chemically diverse than in the cradle of our solar system. In such an environment, carbon dioxide could freeze in massive layers, building comets rich in CO2 while leaving water ice buried or sparse. The comet that would one day become Atlas grew there, layer by layer, until the chaotic gravities of giant planets or passing stars flung it into exile. If this is true, then Atlas is not just a comet, it is a time capsule, a messenger carrying the fingerprint of another system. Its chemistry is like a cosmic postcard, stamped with the conditions of a nursery we will never see directly. By studying it, astronomers are given a rare chance to peer into the diversity of planetary systems across the galaxy. The implications ripple outward. If Atlas formed in such a cold, CO2-rich environment, then its parent system may have planets with chemistries very different from our own. Worlds with atmospheres heavy in carbon dioxide, perhaps, or icy giants with volatile rich moons. Each comet ejected from that system carries a hint of these worlds, drifting across interstellar distances to share their secrets with distant observers like us. Of course, the picture remains incomplete. We cannot trace Atlas's path back to its origin. The galaxy's gravitational tides have erased its birthplace, scattering it beyond identification. All we can do is read its chemistry and imagine the nursery it once called home. Was it a young, bright star with abundant volatiles, or a dim red dwarf, cold enough to preserve exotic ices near its heart? The comet's composition leaves us with possibilities, not certainties. But perhaps that is enough. The very existence of Atlas reminds us that the galaxy is not uniform. Each stellar nursery is its own experiment, each comet a frozen record of that experiment's results. By comparing Atlas with Borisov, with Oumuamua, and with the comets of our own solar system, we begin to see a spectrum of diversity, a gallery of alien formation zones painted across the Milky Way. For the dreamer, this is a soothing thought, the idea that every comet is a message, every fragment of ice a whisper from another star. Atlas is more than just a visitor, it is a storyteller from afar, carrying tales of a nursery we will never walk beneath, but which still speaks to us through chemistry, light, and silence. Some suggest its coma may exaggerate apparent mass. Dust can make a small object appear like a giant. When we look at comets, what we see is not the nucleus itself, but the luminous veil of gas and dust that surrounds it. This veil, called the coma, glows brilliantly in reflected sunlight, spreading out to dwarf the solid heart hidden at the center. In some cases, the coma can extend hundreds of thousands of kilometers, transforming a nucleus no larger than a mountain into an apparition the size of a planet. For Atlas, this has led some scientists to caution. Perhaps the comet only appears colossal. Perhaps dust, not mass, is the true cause of its grandeur. The problem lies in interpretation. Brightness alone does not directly reveal size. A tiny nucleus shedding large amounts of dust can look just as impressive as a larger nucleus with modest activity. To the naked eye, or even the sharpest telescope, the difference is not obvious. Models must be built, assumptions made. And it is here that debate flourishes. If Atlas's coma is unusually dense with dust, its apparent immensity could mislead us, inflating estimates of its size and weight. Astronomers point out that comets are notoriously fickle in their behavior. Some release vast plumes of dust when surface layers crack, creating temporary bursts of brightness. Others remain dark and quiet, betraying little of their presence. If Atlas happens to belong to the more active category, then its glowing shroud may exaggerate its importance. In this view, the comet could be smaller, more ordinary, its apparent mass a trick of perspective. Yet this explanation does not settle the paradox. Even if dust makes the comet look larger, it does not account for its motion, or rather, its lack of deviation from gravity's pull. The coma can mislead our eyes, but it cannot mask acceleration. The absence of measurable orbital shift still suggests heft, no matter how dazzling the dust. Thus, while dust may exaggerate the comet's appearance, it cannot fully erase the argument for an unusually massive nucleus. Still, the image of dust as a mask carries power. It reminds us that appearances can deceive, that what shines most brightly may not reveal the whole truth. It also highlights the challenges of astronomy itself. Peering across millions of kilometers, through veils of gas and cosmic interference, to measure something hidden within. Like trying to judge the size of a candle behind smoke, our conclusions are always softened by uncertainty. For scientists, this means caution. For dreamers, it means wonder. A comet wrapped in a mask of its own making becomes a metaphor for mystery itself. Atlas is both what it shows us and what it hides, both the glow of its coma and the stone at its center. Perhaps, in the end, the truth lies between extremes. Dust may exaggerate, but mass still matters. Atlas may be neither as ordinary as skeptics suggest, nor as extraordinary as its boldest advocates claim. Instead, it may be exactly what comets so often are: enigmatic, deceptive, and endlessly compelling. A puzzle that reminds us how easily light and shadow can play tricks upon the human mind. Brightness can be a trick, but acceleration, or the lack of it, cannot lie. Astronomy often wrestles with illusion. A faint star may appear dim because it is far away, not because it is small. A galaxy may seem tiny, when in truth it is vast and simply distant. Comets, with their glowing comae and sprawling tails, are masters of deception. Dust can veil the nucleus, exaggerating its size, creating the illusion of enormity where only modest mass resides. Yet, when it comes to motion, illusion fades. Gravity and acceleration speak in absolutes, and it is here that Atlas's secret begins to emerge. The reasoning is straightforward. A comet that vents gas into space produces thrust. That thrust, no matter how subtle, should alter its orbit. Even a small nucleus, shedding vapor unevenly, should wobble like a boat rocked by gentle waves. Astronomers track such changes with exquisite precision, mapping each shift in trajectory, each deviation from the expected gravitational path. But Atlas does not wobble. Its course is steady, unyielding, and entirely gravitational. The absence of acceleration becomes, paradoxically, the loudest signal of all. This is why mass matters. Dust can exaggerate brightness, but it cannot disguise inertia. For a comet's venting to fail at moving it, the comet must carry enormous weight. The Harvard team treats this as a kind of cosmic scale. The jets provide the push, and the absence of response reveals the body's true heft. In this way, Atlas's stubborn orbit becomes a measurement, not of light, but of resistance. Of course, critics point out the assumptions. Perhaps the gas vents in perfect symmetry, cancelling thrusts before they can register. Perhaps the velocity of the escaping molecules is lower than expected, producing weaker forces than our models allow. These possibilities cannot be dismissed, and they remain active parts of the debate. But symmetry so perfect, and outflow so consistently weak, stretch probability. The simpler explanation, as Loeb's team insists, is that the comet is too massive to be nudged. This approach, letting motion arbitrate truth, illustrates the elegance of celestial mechanics. Light can deceive, brightness can mislead, but the laws of dynamics remain impartial. They do not bow to illusions. Just as a feather and a stone fall at the same rate in a vacuum, a comet cannot fake its inertia. What Atlas shows us is not in its glow, but in its refusal to deviate. For listeners drifting into calm reflection, this truth carries a certain comfort. It reminds us that in a universe filled with uncertainty, there are still anchors, principles that cannot be tricked by appearance. And through these unwavering measures, we glimpse the true character of an interstellar wanderer. So while Atlas dazzles us with a radiant mask of dust, the deeper truth lies in its silence, in the way it glides untouched along its orbit. No illusion of light can change that. Beneath the veil, the comet's mass stands revealed, steady and undeniable, a mountain adrift among stars, immune to deception, answering only to gravity itself. For every paper raising the comet's size, another emerges urging caution. Science thrives on this tension. Astronomy, like all science, is not a monologue but a dialogue. One team advances a bold claim, another responds with skepticism, and still others refine the data in search of clarity. With Atlas, the divide is becoming sharper with each new observation. Harvard's team insists that the comet's immense mass explains its refusal to accelerate, while other groups argue that uncertainties in gas outflow, dust production, and modelling could account for the same observations. This back and forth is not weakness but strength, the very heartbeat of discovery. At the core of the divide lies methodology. Loeb, Cloaked, and Verres treat the absence of non-gravitational acceleration as decisive evidence for heft. Their critics counter that such inferences rely on assumptions about outgassing that may not hold. If the gas escapes more gently than expected, or if jets align symmetrically, then the comet's motion would remain steady even without extraordinary mass. Both interpretations are plausible, and the data, so far, do not fully close the case. In this way, Atlas has become a mirror for scientific philosophy. On one side stand those who argue for boldness, who believe that anomalies should be taken seriously, even if they stretch models beyond comfort. On the other side are those who argue for restraint, who insist that until uncertainties are eliminated, extraordinary conclusions should remain on hold. The tension between these approaches has played out before, most notably during the debates over Oumuamua, and now it repeats with a new interstellar guest. For the public, this divide can sometimes seem like conflict. Headlines frame it as disagreement, as factions battling over what is true. But within science, this is how knowledge grows. Disagreement forces better measurements, sharper models, and deeper thought. Each critique is a whetstone, sharpening the edge of inquiry. Atlas, massive or not, has already served its purpose by igniting debate that will refine our understanding of comets for decades to come. The widening divide also reminds us of the human side of science. Researchers bring not only data but also perspectives, biases, and temperaments. Some are drawn to bold hypotheses, others are cautious by nature. Together, they create a balance, ensuring that science does not leap too quickly into fantasy, nor retreat too timidly from possibility. The comet, drifting silently through space, does not take sides, simply continues on its path, leaving us to interpret its meaning through our own lenses. For those listening in the quiet of night, this divide is not a clash but a harmony. Just as music requires tension between notes, science requires tension between ideas. Without challenge, discovery would stagnate. Without imagination, it would wither. Atlas, in sparking division, unites us in the deeper goal, to know the universe more truly, even if certainty takes time. And so the scientific divide widens, not as a rift to fear, but as a fertile ground from which clearer understanding will eventually grow. It is the patient rhythm of progress, echoing across generations, reminding us that knowledge is not a single voice but a chorus. Perhaps Atlas reminds us how little we know of the galaxy, how vast the unknown remains. Astronomy is often painted as a triumph of knowledge, the discipline that measures galaxies, weighs stars, and predicts eclipses centuries in advance. Yet beneath its precision lies humility, a quiet acknowledgement that most of the universe is still uncharted. Each new discovery, rather than completing the map, expands its borders. Atlas is one such discovery. It drifts across our skies, not as confirmation of what we know, but as a reminder of how much we do not. The comet's mass, its chemistry, its paradoxical stillness, each raises questions that unsettle our models. Are interstellar giants common, or is Atlas a rare outlier? Do other stellar nurseries forge comets rich in carbon dioxide, or is this body unique? Why do our predictions falter when tested against its stubborn orbit? Each unanswered question humbles us, reminding us that human knowledge, vast as it seems, is only a faint light in an immense darkness. This humility is not defeat. On the contrary, it is the essence of science. To admit ignorance is to keep the door open to wonder. The galaxy is not a solved puzzle but a living mystery, and every object like Atlas nudges us toward deeper curiosity. The lesson is not that we know too little, but that there is always more to learn. Humility also extends to perspective. Our species has existed for only a blink of cosmic time. Our telescopes have watched the skies for just a few centuries. The fact that we have already seen 3 interstellar visitors is extraordinary. But it is not the full story. Countless others must have passed unseen before we had the tools to notice, and countless more will pass long after we are gone. Atlas humbles us by placing our moment within a continuum far larger than our lifespans. There is also humility in scale. Tens of billions of tons of rock and ice glide effortlessly across the void, indifferent to our debates. We can calculate its orbit, estimate its chemistry, even speculate about its origins. Yet the comet itself carries on, unmoved by our attention. Its journey is not about us. We are incidental observers, privileged to glimpse a fragment of a story billions of years in the making. For the listener, this humility can feel soothing. It is a reminder that the weight of the cosmos does not rest on our shoulders. The universe does not demand that we solve it all at once. It invites us simply to watch, to wonder, and to learn in small steps. In a world filled with urgency, there is peace in knowing that the stars move at their own pace, indifferent to our haste. So perhaps the greatest gift of Atlas is not data or theory, but perspective. It whispers that we are small but not insignificant, that we are learners, not masters, and that the galaxy is vast enough to always leave us humble. Even Harvard's Loeb has flirted with the possibility. A probe? A derelict? The idea sparks wonder, even if it lacks evidence. The suggestion that Atlas might be technological rather than natural is not offered as a conclusion but as a question. Could an advanced civilization deliberately build something so massive, or disguise machinery within layers of ice and dust? Could it be a probe drifting silently through the galaxy, its purpose lost to time? Or perhaps a relic? A derelict no longer active but still wandering on a trajectory set millions of years ago? These questions stir the imagination because they stand at the edge of what we know, balanced precariously between science and speculation. Loeb himself has drawn attention for suggesting that Oumuamua might have been artificial, perhaps a light sail or fragment of alien craft. Atlas is a different case. It shows all the outward signs of a comet, with its coma, its tails, and its chemistry. Yet its mass, if Harvard's estimates hold, feels excessive, almost suspiciously so. A body too large to be pushed by its own jets could, in theory, be designed that way. Mass, in this scenario, becomes camouflage, a way of masking activity and ensuring an object looks unremarkable to anyone watching from afar. Still, imagination must be tempered with reason. Building such a body would demand resources beyond our comprehension. Billions of tons of material, carefully assembled, then launched into interstellar space. It strains belief. And yet, to civilizations millions of years older than our own, what seems impossible to us might be trivial. Just as ants cannot fathom skyscrapers, we may not be able to fathom the engineering feats of others. The attraction of the technological hypothesis lies not in its likelihood, but in its poetry. To think of Atlas as a vessel makes us reimagine the comet as more than ice and rock. Suddenly it becomes a story, a messenger sent across the stars, or a time capsule drifting between civilizations. It invites us to see ourselves not just as observers of nature, but as potential participants in a galactic dialogue. Even if the idea lacks evidence, it carries symbolic power. Critics rightly remind us that extraordinary claims require extraordinary proof. Every measurement of Atlas can still be explained within natural frameworks. Chemistry, formation zones, ejection dynamics. To leap to technology is to risk overshadowing the extraordinary reality of nature with speculation. A giant interstellar comet is wondrous enough without gilding it with artificiality. And yet, the idea lingers, not because it is proven, but because it resonates. It reflects our yearning to know whether we are alone, whether intelligence has flourished elsewhere in the galaxy. Each interstellar visitor becomes a canvas for that yearning, a chance to imagine connections that stretch beyond our world. So, what if Atlas is technology? Perhaps it is not. Perhaps it is only ice, rock, and dust. But in asking the question, we glimpse the depth of our curiosity, the very trait that propels us to watch the skies, to study the unknown, and to dream of companions among the stars. We search for meaning, even in ice and dust. Sometimes the patterns are real, sometimes imagined, but always powerful. It is a trait woven deep into our species. From the first constellations mapped across the night sky, to the equations that now describe gravity and light, Humans have always tried to turn chaos into order. When we gaze at Atlas, drifting silently between the stars, we cannot help but look for patterns, clues about its origins, signals about its purpose, evidence of its meaning. Some see chemistry and dynamics. Others see the possibility of engineering. Both views spring from the same instinct, the desire to weave the unknown into a story. Patterns have always been our bridge to understanding. Ancient astronomers noticed the regular rising of Venus and turned it into myth. Modern astronomers noticed the wobble of distant stars and turned it into proof of exoplanets. Each step in science is born from pattern seeking, from the ability to see rhythm where others see noise. Yet this gift also carries risk. Our minds are so eager to connect dots that we often invent constellations where none exist, hearing messages in the static of the universe. With Atlas, the pattern-seeking instinct is on full display. Harvard's team sees consistency in its unchanging orbit and interprets mass. Skeptics see symmetry in its venting and interpret balance. Dreamers see immovability and interpret intent. Each group finds a pattern, and each story reflects more about us than about the comet itself. It is as though the icy traveler has become a mirror, showing us not only the universe but also the way our minds work. This is not a flaw, it is the heart of science and imagination alike. It gives direction to our questions, structure to our theories, and beauty to our wonder. Even when we are wrong, even when the patterns dissolve under scrutiny, the act of searching pushes us forward. Consider the paradox. If we never sought patterns, we would never discover truth. But because we do seek them, we sometimes see more than is really there. Science thrives by holding both sides of this paradox at once, welcoming imagination, yet testing it against evidence. That tension is what drives progress, and Atlas is a perfect example. For listeners drifting into reflection, this trait of ours may feel strangely comforting. To know that humans have always looked upward, tracing lines between stars, weaving stories from light and shadow, is to feel connected across time. The patterns we see may shift, myths giving way to measurements, speculation giving way to certainty, but the impulse remains constant. It is part of what makes us human. So as Atlas glides through the darkness, we will continue to search for meaning in its silence. Whether the patterns we find prove real or imagined, they will carry power. They will remind us that we are storytellers as much as scientists, explorers not just of the cosmos, but of the patterns that bind us to it. 3i Atlas will not linger. By next year, it will leave us behind forever. What we learn now may shape our understanding of interstellar space for decades. Every interstellar visitor is a fleeting guest. Unlike the comets and asteroids bound to our sun, these bodies sweep in on open trajectories, paying brief visits before vanishing into the dark. Atlas is no different. Its arc through the solar system is temporary, a graceful curve that will carry it away once more, back into the unbounded night. For astronomers, this impermanence adds urgency. Observations must be made now, before the comet dims, before distance steals its secrets away. The months ahead will be a race against time. Ground-based telescopes will track its motion with ever finer precision, searching for the smallest hint of acceleration. The James Webb Space Telescope will continue to peel apart its spectrum, chasing the mystery of its unusual chemistry. Probes near Mars will watch from another angle, gathering data that Earth alone cannot. Each instrument becomes a participant in this cosmic investigation, each one working to piece together a portrait before Atlas slips from view. What we learn in this short window will echo long after the comet itself has vanished. If Harvard's claims of immense mass hold, we will be forced to rethink models of planetary formation and ejection. If not, the lessons will still be profound, sharpening our methods and reminding us of the complexities hidden in even the simplest assumptions. Atlas may confirm our expectations, or it may overturn them, but either way, it will expand them. The road ahead also extends beyond this single comet. Every observation of Atlas builds experience for the next visitor, We now know to search not only for brightness, but for silence in acceleration. We know to watch for chemical fingerprints that differ from our familiar comets. We know that interstellar objects are not curiosities, they are classrooms, each one teaching us about environments and histories beyond our reach. For the public, the departure of Atlas may pass quietly, a story fading from headlines as it drifts into the void. But for scientists, the data will live on, stored in archives, reanalyzed as models improve, revisited when new interstellar travelers arrive. Decades from now, long after Atlas has become another anonymous speck among the stars, its brief visit will still shape our understanding of the galaxy. For listeners settling into calm reflection, there is comfort in this perspective. Atlas is not lost when it leaves us. It is carried forward in memory, in data, in the questions it inspired. Its road ahead continues across the Milky Way, while ours continues here, with eyes lifted to the sky, waiting for the next messenger. The comet's passing reminds us of the rhythm of discovery, fleeting moments, urgent observations, and enduring insights. The universe does not pause for us, but it does offer windows, short, shining intervals in which we may glimpse its secrets. Atlas is one such window, and the road ahead is not only its journey outward, but our journey inward, toward deeper understanding of the cosmos we call home. And so, as 3i Atlas drifts farther from our sun, we are left with questions that are bigger than answers. Harvard's study suggests a mountain of mass, a body too heavy to be pushed by its own breath. Others urge caution, pointing to dust, symmetry, or the complexities of outgassing. But perhaps that is the gift of Atlas. It is not just a comet, it is a reminder of humility, a reminder that even with our telescopes, our models, and our theories, the galaxy will always hold mysteries just beyond our grasp. Each interstellar visitor carries stories of other suns, other nurseries, other worlds we will never see. In their silence, they whisper of how vast, how diverse, and how surprising the universe truly is. As you lie here now, listening in the dark, let yourself feel that vastness. Picture Atlas gliding on, leaving us behind, still carrying its chemistry, its weight, its secrets. And remember that you too are part of this same cosmos, made of the same elements, bound by the same gravity, illuminated by the same stars. There is peace in this perspective. We do not need every answer to feel wonder. We do not need certainty to feel gratitude. To live in a universe that sends us these messengers even briefly is a privilege. It reminds us that we belong to something immense, something timeless, something beautiful. So let go of the questions for tonight. Let them rest with the comet, far out among the stars. Allow your breath to slow, your body to soften, and your mind to drift. You are safe, you are small, and you are part of a universe vast enough to cradle you gently to sleep.